Yes, good evening, hello, to all of you. So today we will be starting shortly with this, I think the last live session of this course, and we'll wait for some few minutes and then we'll start.
Sir,
Yes,
sir, assignment solutions didn't came, sir, as of now, from week one onwards.
assignment solutions. You didn't get the answers?
No, sir, assignment only after submitting the assignments, we're getting answer. We didn't get any proper solutions like any other
Detailed
courses.
solutions, I don't think you will get the detailed solutions. For that, I think you can see the live sessions which I have recorded and posted on the YouTube. And
Oh,
yeah, they will not give you a detailed solutions. Detailed solutions,
sir, sir, the document also available, sir.
document for
What?
like solution document.
No, no, sir. What and all you went through the live sessions.
Haha.
During the live session, there is a document. Google document is there.
You mean some PDF form where like I have made a
Oh,
PDF something like that?
yes, sir. What you have discussed in the document
Uh,
format.
no, that is not there. Actually, in live sessions, I have revised the concepts from the week, and most of like I have like solved some extra questions and the assignment questions. So I don't think there is a document required because extra questions and assignment question you can see the videos directly and then like get an idea okay how these questions are solved.
Yeah, sir,
So
is there any reference book, sir, which will cover what and all models are present?
reference
Sans, sir.
book, like there are many, but I don't know which for this course which will be there is no set reference book from where you can get the questions, but like but what from where which I was preparing it was it was Sergio Franco like Opam Designs by Sergio Franco I think. So from
Sir, in
where.
example problems, what and all assignment questions, that questions will be present, right?
No, I cannot guarantee the assignment questions were in that book.
Similar kind of, sir, not exactly.
Similar. I think for concept clearing, that book is good, but for question solving, I don't think so. For question solving, just go through the assignments and I will and go through the extra questions which I have solved in the live session. And today also I will solve I think 16 extra questions. So you will get an idea. How the questions will be. So that will help you. So I can only say you can practice from I think from the internet, like you can get like if you will write opamp questions and also then you can get the like which whatever questions you can, but otherwise just go through the content and the assignments and the extra questions which I am like giving. So I think that will be
Hmm.
enough.
Sir, I am registered for the exam also, sir, because that's
I
why.
think next week you have exam.
Yes, sir. Sunday exam.
Sunday. Uh-huh.
Yeah.
Okay, okay. 30th, na 30th April.
Yes, sir. Yes, sir.
Hmm. Just go through the contents like thoroughly. I think it will be fine.
Can I know how many people register for the exam, sir? You have any data?
That I don't know, but I think total students in this course, what I saw that it was I think 1400 to 1500. So, but that I don't know whether all will be giving the exams or not. So that is
Okay, there are enrolled candidates, no, sir.
enrolled. So yeah. So I think so. So I think anyway, I was starting with the revision. So
Sir, one more, sir.
uh,
Sir, for you in campus, you did analog IC design, no? Ragendra Krishna course, sir, course.
analog IC design I didn't do, but yeah, course is there. Course is there. Analog IC design
Sir, could you give any final exam is entire blank, sir? Can I expect any MCQ, sir?
from analog IC design.
Yes, sir. I am parallelly enrolled for that course also. I'm writing exams, sir. As of now, there is only MCQs. In
Uh,
final exam also, in the same way I can get, or can I get MCQ?
I cannot be sure about that, but I think if MCQs were given, so I think that he will follow that format. But I cannot be sure about that. So you will have to see. Because analog
Yes.
IC design, I haven't like taken, I haven't been TA for that course, so I cannot say. Yeah. So okay, so coming back to the course content. So today we will be discussing about the week 12 assignment questions, and or any doubt you have throughout the course, you can ask. I will be solving extra questions also, so you will get an idea how the exam questions will be, and yeah. So if you have any assignment question, first of all, just ask me. Otherwise, I will go through the assignment questions of 12 week 12. And if you have assignment questions before this week also, like any doubt in that, then also you can ask.
Sir, from week 12, I'm confident, sir. I get approximately almost all correct, 9 questions correct.
Yeah, week
From
12
week
is
11, week 11 I didn't get, sir.
week 11. Okay. So
Yes.
do you want me to discuss any question from week 11?
Yeah, sir. I think from week 11, yeah, from week 11, sir.
Okay, week 11.
At least
Okay.
some ideas, sir. I mean, what and all I lacked, no, sir. I will go through it.
Oh, okay. Okay.
Hmm.
So if
To
you have,
understand all the mistakes, sir. That is due to my conceptual understanding might be if I have to refer this thing, you may get idea, no, sir, where I get it mistake.
okay, I should not discuss then week 11 questions?
Week 11 only, sir.
Week 11. Okay, I will go start from week 11, then I will come to week 12 assignments also. Okay,
Yeah,
okay,
sure, sir.
then I will have to open that. Wait, open that document.
Sir, that what and all that PDFs are present, no, sir.
Which one?
This one, sir, your discussion, no, sir.
Yeah, yeah.
Can you share it to us, sir, in chat box because it would be easy for me to refer. I
Chat
will go
box.
through the. Yeah, sir. I mean,
Chat.
there will be a link now, sir. For
Actually, this I have. Okay, wait. Only week 11 solved, like whatever I've mentioned here, that you have to take. You have you need this one, this PDF. Okay, wait.
no, sir. From week one also, you will have like this reference, no, sir.
Oh, from
For
week
every week,
one.
you.
Okay, then I will do one thing. I will share this in the discussion forum, all the PDFs of this assignment questions.
Uh, yeah.
Okay,
Uh,
whatever I have done. I don't know whether you will be able to get this or not, but I will still
mm.
say if you will see the YouTube videos, then it is better.
No, sir. I will go through it, sir.
Okay,
After
okay.
I mean, we get. I mean, time is very less, no, sir. I have to.
Okay,
I
okay.
have
I
to
will
go
share.
for 2 more courses, sir. One is
Okay,
Shanti Bhavan.
I will write
That's it.
this. Wait. I'll share assignment. Oh, sorry. So I think from the starting I don't have, but I think from the middle I started doing like this. So from there I will share this thing, share assignment questions, PDF. I will share this in discussion forum. Okay.
Sir, don't forget, sir. It is very important for me.
Yeah, yeah,
If
yeah.
you will try to share now itself, sir. I will access. If I have any
No,
doubt, I
no, no.
will ask.
I will share. No issues. After the lecture, I will share. Don't worry. I have all the PDFs. I will share that in the discussion forum. Okay. So yeah. So if you don't have any uh, questions in week 12, so week 12. Okay. Anyway, I will just go through the week 12 assignment question. So okay.
Okay, sir, could you start from week 11, sir? You already
Okay, week
started.
11. Yeah, week 11. Okay. So we'll start with the first question. Dash type of DAC requires two set of registers. So they are asking for two set of registers. So we know that. So I think in week 11 I told you about this, like about the digital. What is the basic structure of digital to analog converter, and the
Hmm.
basic equation which we use in this. And then we have basically two types of DAC, that is weighted register DACs and R2R ladder DAC. So weighted register DAC, they have like registers in like two multiple of twos, 2R, 4R, 8R, and so on. But in this R2R ladder, then we have like only R and 2R. So, and the name also suggests that they are having only two registers. So when we see this question, this one, so two set of registers. So I think we can answer that question, R and 2R ladder type DAC. So this is easy. Then yeah. So then dash type of DAC utilizes summing amplifier configuration. So binary weighted, I showed you the diagram of this binary weighted summing amplifier. So they are like we are giving digital inputs like this to to these register 1K, 2K, 3K, 4K, and this is a configuration of summing amplifier. So yeah, so this is the configuration of a summing amplifier. So we can say that okay, binary weighted is type of summing amplifier. So question three is like conversion rate of DAX. So this is so which is having so this is a factual based question. You can you can also answer this question. This is also easy. Then yeah, fourth question. Let an input to a 5-bit DAC is. So they have said that this is an input and the corresponding output is 0.2 volt. Compute the output DAC for an input of 1111. So we have given that for this input in a DAC, we have an output of 0.2 volts. So that this also means this is the least output we can get, least input we can give to a DAC, because all the like MSB is 0 and all the other bits are 0 except the LSB. The LSB is 1 here. This one is LSB. So this we can say this is the lowest input which we can input to the DAC. So for that we have an output of 0.2 volt. That means this is the resolution of this DAC. So if we use this formula, resolution equals to V full scale range divided by 2 to the power n. Then by substituting and getting the final value, we can get the full scale range value. And yeah, they were asking this only. So this is basically full scale, like what will be the value of the DAC when they are making all the input as high. So that is full scale, the full scale. Okay, so this is full scale value, one thing. So then you can whatever the full scale range is, so you can answer that accordingly, this question. So next question was the continuation of this previous question. So they were saying, in continuation to the previous question, comment on the resolution of DAC. So as I said that this is the resolution of the DAC. It's itself mentioned in the question. So you can answer this also. Question 5. Then again, in the continuation to the previous problem, determine the output of the DAC for an input of this. So now we also know that the output of this stack is what, V naught into V full scale range into 2 to the power minus 1, then Bn plus 2 to minus 2, Bn minus 1, so on, 2 to the power minus n, B1. Okay, so this is LSP, this is MSP, this is MSP, this is LSP. So we know that which coefficient is having 1 or 0 value. Accordingly, we can substitute here. So this was the uh, substitution, and then we know the full scale range value. So that is given here. So we can get the answer from there. Okay. So this is also okay. Then the seventh question, compute the percentage resolution for a 10-bit DAC having a step size of 2 millivolt. So if they are asking for percentage resolution, so that is means they are asking with respect to the full scale value. So we have the percentage resolution formula as resolution of the DAC divided by the full scale range of it. multiplied by 100. Okay, so this we have. So resolution, so everything we knew. Yeah, resolution we know. Step size is basically resolution. So we can answer this also. Okay, next question. Digital to analog converter converts binary word to so when we talk about DAC, so either we get a current or a voltage. Apart from that, we cannot get anything else. So if you are getting voltage, we can convert that into current by introducing a resistor. So that is like that's why it can be both current and voltages. Next is select the suitable resistance network for 3-bit 2R ladder tag. So in this just we have to like say which is 3-bit R2R ladder. So in R2R ladder the last this one this resistor is 2K, that is 2R basically, this is 2R, and these are all 2R, and these are all R in between. So based on if we know the structure of the R2R ladder, we can answer this question also. Then we have compute the value of current I for the given circuit. So now for these type of questions, what I have what I will suggest just to go for Thevenin voltage and Thevenin resistance of this whole circuit. Okay, so here also what I did, I first calculated the RTH. So RTH was simply we can uh, ground the input voltages, all the input voltages, and then we can solve for this. So RTH will be like this is 2R, it will be 2R here, then 2R in parallel to 2R, this R, this voltage source we have grounded, and this also grounded, like, and then we are calculating. So this is a very simple network for which we can calculate the equivalent resistance. So we got RTH as 3R. Okay, now the next thing was to calculate this like VTH. So for VTH, it is so for VTH we started from this one. From here we started VTH. So in VTH, we can use n number of ways, nodal analysis, like nodal voltage analysis, or KCL, KVL, whatever you want to, or source transformations, current to voltage, voltage to current transformation, whatever you want to do, you can do in calculating the VTH value. So I did like source transformation, and you can do other things also. So from that, simplified the circuit into this, then I went to this, then here. Okay, then finally I got the VTH value, so that was V by 4, and so finally we got this as the Thevenin equivalent. So RTH was the Thevenin resistance was 3R, and VTH was V by 4. Okay, so then we can easily say what is the current I. So this question I can like say that this can you can expect in the exams also. So this was about this week
We,
week 11. Okay, and so we'll just discuss week 12 assignment also. So sample and hold circuit. So sample and hold circuits are so
uh,
yes,
1 minute.
yes.
Sir, that thermocouple week 8 thermocouple related questions all in recorded lecture, sir.
Thermocouple. Any specific question from assignment?
Yeah, no, sir. In the recorded lectures in the previous problem solving sessions, week 7, sir.
Uh-huh.
And that question will be related to the thermocouple, sir. Wait, sir, just a minute.
Uh, you're talking about assignment questions. Any assignment question or?
Yes, sir.
Okay, week 7. Okay, wait. I will open here. Okay, I think I have maybe. So 1, 2,
Sir,
11.
week 8.
Week 8. Okay. So this 10. This is 9. I think this will be. I don't know whether this is the. Week 8. Huh? Week 8, na?
Yes,
This one.
yes, sir.
Uh,
Thermocouple.
so which question? in this?
Sir, I think we have to go little bit, sir. I think after five.
No, after five. Oh,
Yeah,
this
five,
one.
five.
This fifth one, na?
Yes, sir.
Okay, okay, okay.
5 and 6.
Yeah, so in this, like, what we did actually, so a thermocouple is selected to provide an output voltage for a given temperature. The okay temperature range like zero output it is showing 10 for 10 for 10 degree it is showing 42, 20, 52. So now they are asking the corresponding output voltage for a differential temperature is shown in table. So they are saying differential temperature, okay. So because there are two junctions, so while considering the reference temperature as 0 degree Celsius, so okay, reference is zero. Compute the differential compute the differential output voltage from the sensor for a reference temperature of 5 degrees Celsius. So this is given for 0 degrees Celsius. Now we have to compute the differential output for a 5 degrees Celsius reference temperature. So for 53, like when the reference temperature is 5 degrees Celsius, so and the junction temperature is 53 degrees Celsius. So then what will be the output of this thermocouple? So we have to comment on that. So basically we have the, so from this table, what we can do, we can calculate the sensitivity of this thermocouple. So that is basically delta V, that will change in the output voltage divided by the change in the this what we say the temperature. Okay, so this we have delta VOP divided by delta temperature. So if we say, so we output is like so let's say we from first to data we calculated the sensitivity, that is 42 minus 32 divided by 10 minus 0. So we got the slope of this sensitivity is basically the slope of the like the graph. So this is what basically if we draw a temperature curve and the output curve. So by increasing the temperature we will be getting something like this, because at 0 degree we are getting 32 microvolt and it is keeping on increasing, and sensitivity is the slope of this. Okay, so this is what we calculated. So this is now sensitivity. Now when we have a reference voltage of 5, so what we will do, so we have this data from the somewhat from this table, and we need to calculate this data like the V output divided by, this is the data from our new thermocouple setting, that is when the reference temperature is 5 degrees Celsius and we have to calculate the output. So from here we can, like if we equate these two, the data from this table and the output equation, the sensitivity of the new thermocouple settings, then we can get the output of this thermocouple. Okay, so we have to just equate this thing.
Yes, sir. Sir,
Clear?
I mean, what and all the specific, I mean, for a sensor reference temperature is there, no, sir? That reference temperature divided by that output voltage divided by the reference temperature, and with the data, what and all they provided that
uh,
output voltage by temperature, sir. Here,
uh,
ulta.
no, the output voltage divided by the junction temperature minus the reference temperature.
Okay.
Okay.
Yes, sir. And from the tabulation, okay, yes, sir. Perfect.
Hmm?
Perfect. Yeah. Next question, the only next question.
Next question was like a thermocouple with a reference temperature of 0 degrees Celsius shown an output voltage of 0.8 millivolt for 25 degrees Celsius. So it is for 25 degrees Celsius and a reference of 0 degrees Celsius. It is showing an output of 0.8 millivolt. So let the Seebeck coefficient. So they have given Seebeck coefficient 52 point this. Okay. Compute the unknown temperature if the output voltage is 2.5 millivolts when the reference temperature, now they have changed the reference temperature to 25 degrees Celsius. So now so so what we did in this question, so output they are saying 2.5 millivolts, but we will add so they are saying the reference temperature is 25 degrees Celsius. So in this uh, so see all, so for we have to calculate basically the output at output voltage we have it is being given, yeah, okay, we have to calculate the unknown temperature. Okay, so one thing, what we will do, so see, we have 2.5 millivolt as a output. Okay, first thing. But then we also know that now the reference temperature is set to 25 degrees Celsius. So, and we see that at 25 degrees Celsius, the output of the thermocouple was zero point 0.8 millivolt. So 25 degrees Celsius, the output was zero point 0.8 millivolt. Now, whatever the output we have now, we have added a reference of 25 degrees Celsius also. So this because of this reference, there will be an additional output voltage, and that we already know, that is zero point 0.8 millivolt. So whatever the temperature is, and the output is at 2.5 millivolts. So for this, the total output will be the output added, the reference output also added into this, the output voltage at that unknown temperature. So what we are getting actually, so V output is 2.5 millivolt, which we already had 2.5 millivolt in the question given. And for this reference set, that is 25 degrees Celsius, what was the output? It was zero point 0.8 millivolt, because it is given in the question. Okay, so we have now the total output. The total output, because of this reference voltage, it is 3.3 millivolt. Okay, now we have 3.3 millivolt, and if we use this equation for this one, like temperature equation, like coefficient, Seebeck coefficient multiplied by T minus reference temperature equals to 3.3 millivolt. If we solve this question, if we solve this equation, then we'll get the T, because alpha we know, alpha is 52.17 microvolt per degree Celsius. Okay, so basically, whatever the reference temperature, now see, in these questions what is happening, your reference temperature is getting changed. Okay, so accordingly you have to see what will be output. So now they have said that for output voltage, for some unknown temperature, you were getting some 2.5 millivolt of output. But for that, like they set some reference voltage also. Okay, and that reference temperature, sorry, reference temperature, and that reference temperature was 25 degrees Celsius in this case. And we know for 25 degrees Celsius what is the output, that is 0.8 millivolt. So then we added this at the output, and based on that we will calculate what is the temperature now. Okay.
Sir, first first we need to, could you, I mean, from the reference from the output voltage to that relation from that reference temperature, and we need to form that equation that with Seebeck effect, T
Hmm.
minus.
Ha ha ha. So see, this is the equation, that is alpha multiplied by the temperature, junction temperature, minus the reference temperature, is equals to
Mm.
the output voltage. So since we are taking in consideration this reference temperature also, that's why in output, this output, we cannot write it as 2.5 millivolt only. Because why? Because now we have a reference temperature of 25 degrees Celsius. So some output is being added from this reference temperature also. Okay,
Ah,
so
yes, sir, that was a diagram. Oh, yeah.
that's why we added this at the output, and now our total output is not 2.5 millivolt, it is 3.3 millivolt, because zero point 0.8 millivolt is being added due to reference temperature of the junction. Okay.
Yes, sir. Yes, sir. With this, we will get to 3.3 millivolt. That means the T minus 25 degrees is equal to 3.3 millivolt, sir.
Yeah, yes, yes, yes.
And T is equal to 3.3 by 25.
Now alpha is also there. So 3.3 milli divided by alpha, then we'll add 25 on that.
Okay, alpha coefficient is given, no, sir.
Alpha,
Seebeck
alpha.
coefficient is 52.71
Yeah, yeah,
microvolt.
microvolt per degree Celsius.
Yes, perfect, sir.
Okay.
Sir, okay,
Yes.
sir. With this, I'm perfect, sir. Only question I have doubt, sir. Everything is perfect, sir.
Hmm.
From week 10.
Week 10. Okay, wait. Week 10. Week 11, this is. Okay, week 10, I'll open. Wait. Week 10. I think this is week 10.
This is final, sir. Rest of them are perfect, sir.
No
Only this
issues.
final.
Ask as many as doubts you want. You can. Yeah, week 10. Yeah. Tell me. Which
Sir,
question?
from week 10, yeah, from two, sir. Sir, we start from one onward, sir.
One.
This week I didn't get, I'll get least score, sir. 40.
Okay, I think there was some issue in this. There was some issue, na? You said like this for. Okay, okay, I will tell. So question
Mm.
one, which of the following statement are true? The analog multiplier output should retain in four quadrant and four quadrant one ideally. Log anti-log multiplier single quadrant operations. So this is correct. Like the analog multipliers should be like we ideally we need a four quadrant analog multiplier. Okay, because in that we have the freedom to give the input as plus minus. We give our input Vx and Vy can be plus minus both of both the polarities. So that's why it is good to have four quadrant. So ideally we need that. That is there. And log anti-log multiplies a single quadrant operation. Yeah, I think this was covered in the course itself. The second one. So this is okay. Okay, statements are true. So these factual questions, I think if you fact these questions will only come whatever is being covered in the lectures, and like applying like the concept where you have to apply your mind, that can be difficult. But if you have gone through the content of the course, then you will be able to answer these factual questions. Okay.
Yes, that
Hmm.
factual questions I did, sir. I mean, what
Okay.
I
This
come
one
to
and
this with
next. Okay. Next should I go?
for three
Huh?
questions I am correct. Perfect, sir.
Second
But
also.
yeah, sir. Second also okay, sir. But
Uh.
if I get your approach also, I get some idea, no, sir. That's why I'm
Okay,
saying.
okay, okay. Okay, so second question. Okay, second question is design an analog multiplier to give an unsaturated output. So we need unsaturated output. Okay, if the operating voltage of the circuit is provided with, okay, and the internal reference voltage Vref is set to 10 volt. So reference voltage is at 10 volt, and compute the condition for Vx and Vy. Let Vx be at the inputs to the. So they are saying like what conditions for Vx and Vy we should keep so that the op amp, the analog multiplier will not go into like saturation mode. So for that we know the equation Vx Vy divided by V reference equals to V output. Okay, now we have this thing Vx Vy reference voltage is 10 and we need this to be less than 15 volts because the maximum supply which we are giving to the analog multiplier is 15, so it should be less than 15 volts. So the whatever the this equation, okay, from this we got this. So now we got that Vx and Vy should be less than 150 volts. Now if we see these options, so what we will observe like Vx. So let's say if we go with the first option, sometimes if we like go we have some like answer, we can now start from the like these options also, and we can what we can remove the wrong options based on our logic. So first if we see, so Vx greater than 10, Vy greater than 10. Okay, so if Vx is greater, it is any value greater than 10, then it can be 50, it can be like anything. Let's say it is 20 volts. Vy is also 20 volts. Then this cannot be less than 150 volts in that case. Then Vx into Vy will be 400. Okay, so this we cannot use this. So second options Vx less than 10 volt, Vy greater than 10 volt. So if Vy is greater than 10 volt, again this will uh, like spoil our condition. So but if we see the last option Vx less than 10 volts, Vy less than 10 volts. So see less than 10 volt means maximum, let's say they are on 10 volts. So that means maximum this thing can go to 100 only, which is anyway less than 150. So this condition is satisfying our main condition what we achieved. Okay, so that's why we can that's how we can solve this question. Next question. So what is the minimum number of comparators needed for a 10-bit flash type D and ADC? So this is very easy. You have this if you know the formula you can answer this 2 to the power n minus 1. Okay, then let the current flowing through the circuit is measured using a zero point 0.1 ohm resistor. So there was some issues in this question, but anyway, if we just go simply like current flowing through a circuit is measured using zero point 0.1 ohm shunt resistor. Voltage of the resistor is, so they are simply, so if some current is going through this, so whatever the voltage will be that is IR. So that will be simple Ohm's law based question is this. So this is very easy. Okay, so V equals to IR. So it will be linearly proportional to the current through the circuit. Simple. Now the second question. Based on the previous question, in continuation to the previous problem, that the current through the circuit is to be represented using a voltage display module in which 1 volt input is represented as 1.00 volt. So they are saying this is represented 1.00 volt, because now they are like using a let's say any digital meter or something, for where they are like showing this whatever they are getting. So suggest a suitable method to represent the current reading using the display. So now we saw that we have like the point 0.1 ohm. Wait. So we see here that we have a what uh, we have a we have a resistor, shunt resistor of zero point 0.1 ohm. So now any whatever current we are getting, we have a voltage or voltage drop of zero point 0.1 into I, that is zero point 0.1 into this current. So now based on the options, let's see the drop across the resistor measured using an instrumentation amplifier having a gain of 1. So they are saying that they can introduce an INA, that is instrumentation amplifier, and then they can get they will set a gain of 1 there. Okay. Second option is they will set a gain of zero point 0.1. Third option is they will set a gain of 10. So I think if we go with the third option, so we already had a very less value, that is zero point 0.1 into I. So what will happen if we get, like introduce a gain of 10, then this will become only V equals to I. Okay. So we have increased the gain of this. So if the I is 1 ampere or something, then we can easily display that as that as 1 volt. So based on the options, C will be the right option, the right answer for this question. Sixth question, in conditional problem 4, let the output drop across the resistor is acquired using a 3-bit ADC. Okay, so now they are acquiring this as 3-bit ADC, uh, having a reference voltage of 5 volt. So this ADC is having reference voltage of 5 volt. If the maximum current through the circuit is 1 ampere, compute the level of ADC, the input signal will match. So now we have 1 ampere maximum current, resistor we know. So the drop is what? Zero point 0.1 volt. Okay. So now we have a 3-bit resistor. So the resolution, so resolution if we calculate. So we have the reference voltage, that is 5 divided by 8. So we got point what 0.125, 0.025, no, 0.125. Okay, this is 0.125. Now we have a drop of zero point 0.1 volts. Wait, 5 by 8, how much? 8, 158. Sorry, this is not 15 to 60. It's 625. This is 625. Okay, this is 0.625. So if we have a 0.625 minimum value which this ADC can show, that is 0.625 volt. So what we are getting here is zero point 0.1 volt only. So it is even less than the resolution of the ADC. So we will not get any, the ADC will not be able to quantize this value. So that's why it will show the zeroth level. Okay. If it would have been greater than 0.625 volts, then we can say it would have been at the first level, or the whatever the like corresponding level. Okay, this question is fine. Next question. In continuation to the previous problem, select your approach for representing the current through the circuit with a resolution of 125 milliampere without changing the resolution of ADC. So now they don't need to change the resolution of the ADC. So they are saying that what thing we should add in between the ADC and our circuit, our main circuit, so that we can measure the current of 125 milliampere. Okay. So because initially the maximum current is what? It is 1 ampere. Now they are saying, yeah. Now they are saying they need through the circuit the resolution of 120. So they need a system where the minimum value of the resolution of this current circuit with the resolution of 125 milliampere they can measure. Okay, so let's say now we are giving a current of 125 milliampere. We have a resistor of zero point 0.1 ohm. Okay, so what will be the drop will be 12.5 millivolts. So now let's see the options. Reducing the ADC reference voltage to 1 volt. So if we will change the ADC reference voltage, then its resolution will change. I think we cannot then do this, because they are saying without changing the resolution of ADC. Next question, changing the shunt resistor to 1 ohm. If we change the shunt resistor to 1 ohm, then Then what will happen? So it will be 12.5. This will be what? 125 millivolts. And 125 millivolt, that is like 0.125 millivolt, 0.125 volt. And we know the resolution of this ADC is what? 0.625 volts. So this also it cannot measure. Getting my point? If you have any doubts in between, just like like just ask me. Hmm. So second option also cannot work here. So now they are saying applying the voltage drop across the resistor with a gain of 50. Now they are saying it like introducing this question mark, this block as gain of 50. So what will happen if we introduce this? Then we were getting a 12.5 millivolt of voltage drop using zero point 0.1 ohm shunt resistor and 125 milliampere. So if we multiply 50 with this, then we will get 0.62 volts. So then we'll get 0.625 volts. Okay, so that means this is the minimum value of current which we are giving, that is 125 milliampere. And if we provide a gain of 50 in between the ADC and our system, then it will amplify the minimum value of the current, or we can say the voltage, that is from 12.5 millivolt to 0.625 millivolts. So this is the minimum value of the ADC which ADC can measure. That is the resolution of the ADC. So we haven't changed the resolution of the ADC, and at the same time, we are able to make we are able to measure the minimum value of the current from the circuit by introducing a gain of 50 in between. Okay. So this was about this question, seventh. Any doubt? If you have any doubt, just ask me. I'll repeat it again. Okay. Next question.
Question 7, sir. Only question 7, sir.
Again.
That will be.
Okay. Wait. I will just clear this and again I will just. Hmm. Okay. See, we'll read the question slowly. In continuation to the previous problem, select your approach for representing the current through the circuit. So we first of all we have a circuit like this. We have a zero point 0.1 ohm resistor, shunt resistor, and we are sending some current through it. One thing. So this circuit with a resolution of 125 milliampere. So this is one circuit. Okay, this is one circuit, and they are saying this should have a resolution of 125 milliampere. It means that the minimum value of current which this circuit should measure is 125 milliampere. So the minimum value I minimum can be 125 milliampere. So till this we are clear. Okay, so they are saying they need to represent a circuit. They have a circuit where the minimum value of current can be 125 milliampere. That is the resolution. Okay, now the corresponding bit. Now after this, now they are saying this should be the minimum value of the current, and now they are saying they have to measure this without changing the resolution of the ADC. So in this previous question, what we were doing, we were just connecting after this an ADC. But now we cannot measure this value. Why we cannot measure this value? Because if we see the voltage here, what is the voltage here? That is 125 milliampere into zero point 0.1 ohm resistor. That is 12.5 millivolts. But our resolution of ADC is what? 0.625 volts, and this is 0.025. This one. Okay, so our resolution, our ADC can start measuring only when the voltage reaches to 0.625 volts. Okay, so but our minimum value from the circuit is coming as only 0.025 volts. So this we have to we have to introduce something extra in between these two, so that we can make this value in it's comparable to this the minimum value which the ADC can measure. So let's say we remove this ADC from here. Okay, we introduce some black box here. We don't know what it is. After that, we are using the ADC as itself. Now Now what is happening? This ADC is having a 0.625 volt of resolution. So something we should do here in this black box, so that the minimum voltage which this circuit is outputting, that is 0.025 volt from here, 0.025 volt, it should get amplified to 0.625 volt. Why? So that this ADC can measure that easily. So for that, let's see the options. How we can do this. First of all, they are saying reduce the ADC reference voltage. So we can do this, but what will happen? But there is a condition in the question that we cannot change the resolution of the ADC. So this we can remove this option. This will not be the answer. Second, change the shunt resistor to 1 ohm. So even if we change the shunt resistor to 1 ohm, then what will happen? Then also the output will be 125 milli into 1. That will be 0.125 volts. Then also it is not comparable to the minimum value which the ADC can measure. That is 0.625 volts. So this also option we can remove. Now the next option is amplifying the voltage drop across the resistor with a gain of 50. Now they are saying, can we amplify this, whatever the voltage, the minimum voltage drop was 0.025 volt. If we can amplify this with a gain of 50, then what will happen? So then 0.025 into 50 will be what? 0.625 volt. So this black box introduced a gain of 50, which made the voltage here as 0.625 volts. So this voltage was given when we introduce a minimum current of 125 milliampere, and now this ADC can measure that easily. Okay. So by introducing a
Yes, sir.
gain of, now you are clear?
Yes, sir.
Okay, okay. So this was this question. So if others also have some any doubts in any assignment questions from any week, then you can ask me. And anyway, I will after some time I will solve some extra questions that can be useful for your exams. Okay. So I'm just going through the assignments. So eighth question, in continuation to the previous problem, compute the level of ADC when the input current is zero point 0.5 ampere. So now they say that they have a zero point 0.5 ampere current, resistor is this one zero point 0.1, and we have a gain of 50 there. So final output will be 2.5 volts. So we know that 0.625 volt is the resolution of the ADC. So if we keep on increasing, we will get that it is, I think, at the fourth level. So that is also, that is easy then. So now next question, a 0 to 10 volt sine wave signal is connected to an ADC which has a reference voltage of, okay, minus 10 to 10 volts. Select your approach to maximize the use of resolution. So now they are saying that they have to measure a signal of 0 to 10 volts sine wave signal. So now connected to an ADC. So this ADC is having a reference voltage from minus 10 of minus 10 to 10 volts. So now they are giving some of the like options how we can do that. So first option is by amplifying the input signal with a gain of 2. So if we amplify the input signal with a gain of 2, then it will be from 0 to 20 volts. Okay, one thing. Second is by attenuating the input signal by a factor of 2. See, this we cannot, attenuation we should not do, because then we may lose some information. So this way we cannot go. Third is by varying the reference range of ADC to 0 to 10 volts. So they are saying to reduce the like the range of the ADC. But why should we reduce the range of ADC if we are like if we can do that without that by increasing only the gain of the signal, that is by amplifying the input signal. So that is like so if we increase the gain of the signal, then we can like measure the signal. Okay. uh, yes. Okay. So yeah, next question, a flash ADC is I think, yeah, it is. I think the fastest ADC
Okay.
which we have, and it is having this. This is factual based question, so this is also easy. Hmm. So I think this is also fine. So now, yeah. So now I have some extra questions. I think we can solve that. It will be good if you can just. Uh, so I so I think while I'm like I will solve, so you can also think. So and you can also answer in the chat box, or you can open your mic if you want. Okay, so we'll start with these questions. The first question is at what condition? So these are all extra questions. Wait. By the way, if you have any doubts in the assignments, which from till week 12, so then you can ask me. If not, then we can go start with this extra questions. Okay. In between, if you like, if you come to know about okay, some doubt was there, so then you can just like just stop me and ask me. Okay, no issues. Yeah. Now, first question. So, at what condition the digital to analog conversion is made? So this question is basically saying at what condition this binary counter will stop counting, and at that moment it is then it is saying that okay, now the conversion has been made. I will not count anymore. So what will be the condition for that? You just think, and if you have any answer, you can write down in the comment box, or you can speak also.
Sir, VA should be greater than VD, sir,
Why?
because it will generate VA is the input of the op amp. It is applied to the non-inverting terminal, right? If a non-inverting terminal is greater than the inverting terminal, then it will produce a positive voltage, and positive
ठीक है.
voltage will produce a, yeah,
Okay.
right. And that if both clock and VSAT are positive, then and gate will be active, right?
Okay, one will go. So it will
Yeah.
activate the binary counter then, na? It will not
Yes, sir. But
stop the. It will see. I am saying, see the question. What condition design conversion is made? It is done. It is stopped now. It is not showing it will start. It is not saying when it will start. It is saying that when it will stop.
okay, okay. Then it should be VA is less than VD, sir.
Yeah, yeah, yeah. So this should be the answer because the approach was same. Only the we should like read the question also properly, like thoroughly. What it is saying, it is made already. It is done. So if we have VA less than VD, then this will be minus VSAT. Then this is minus. Then we will get zero, and this will stop the binary counter from further counting. Okay. So then we will get okay. The counting has been done. Okay. Any doubts in this question?
No, sir. For
Okay,
me.
others also, if have any other doubts, then yeah. Yes. Okay, we'll go with the next question. So just read the next question. So if I input is VA at VA is one. So here we are giving 1010. Then find the correct conversion sequence for the given circuit. Okay. So I will. So there were options. I removed the options just as to increase the complexity of this question. But based on the options, you can answer this question. So I will make you clear, like make this thing easy for you. From next question, we will like ask. Okay, but I will tell the answer for this. So let's see. As successive approximation, this analog ADC, what it does, like it starts from the middle value. If it is 4 bit, then it start from the 1000. Okay, so now it will start from 100. So now we have 100 here. So this is 10000. Here it is 10. So this 1010 is greater than 1010 is greater than 1000. So I can say this is SAR output, or we can say this is DAC output basically because it is giving to the DAC. So DAC output, okay, and Then there is a comparator output. Comparator output is this one. This is a comparator, na? Comparator. Okay, so this is a comparator output. So we have 1010 greater than 1000. So comparator output will be what? It will be 0. Okay. Uh, yeah. Okay. Yeah. One clarification. This is plus. This is minus. This question. So yeah. So this will be what? If this plus side is more than this negative, then it will be 1. Okay. Then what will happen? When the comparator gave that one input to the SAR, that means this bit will come as it is. This will bit will become 1. This will be 0 0. Okay. Then what will happen? Now this 1100 is greater than 1010. Okay. Then our comparator output will be what? 0. So what will happen? This will remain as it is, but since this the output was 0, so this bit will become 0. It will automatically activate the next bit as 10. Okay. Now this 1010 is equal to 1010. So that means comparator output will be what? 1. So this will be remain this will remain this it will make this 1 only because we got one output, and it will activate this as 1, the last bit. Okay, so then what will happen? This 1011 is greater than 1010. Then it will be 0. So we got an output of 1010. So if we gave an input of 1010, this thing here, it gave an output of 1010. Okay. Okay. If you did you understand this thing?
Yes, sir.
Okay, now for others also fine.
Like, I didn't understand what SAR is doing.
SAR is basically see. Uh, so we gave an input of 1010. So we have to, so this is some what we say, it is some voltage value. Okay, this although it is 1010, but let's say if we had some this is basically a binary, we are seeing a voltage value in a binary form, that's all. So this R, what it is doing, so whatever voltage we gave here, it is converting that into bits, this MSP, like into digital form. It is ADC, na, analog to digital conversion. So what is happening?
Yes.
So whatever input we give, so this with the help of this SAR and this DAC, it is an closed loop system. So if we are giving 1010, this SAR will automatically, like, and this SAR in with the help of this comparator, it will automatically stop at this output, at this input whatever. So if we got this 1010 at this output, then it will stop this thing. Okay, so this system is like that, the closed loop system. So this is basically a binary version of a decimal value input. So this DAC is converting whatever the SAR is outputting, it is converting that into analog value. This is analog. It is then being compared with whatever input we were giving, and then it is again then changing the SAR digits, like these digits. And once it achieves 1010 here, like, so then it will stop that thing. Okay.
Okay.
Initially, why DAC output is 1000?
uh, it was at the midnight. It will not always be 10, only at the first stage it was 1000.
Yeah.
After that it will be this, after that it will be this and this. Okay, it is like that, it is
If you enable
keeping.
start, then we'll get 100.
How what?
If we enable start signal, then it will get
SARS.
100. Is it?
Starting from the starting. And just keep in mind the SAR starts from the middle value. So from the middle value, either it can go up or it can see, it is like this 1000. If the value is higher than this, it will go up, it will make the other bit active, 00. like this. If it is less, the value is less than this, then it will be 1 0. Then it will make this bit active, then it will be 1 0. But if it was higher than this, then it will be 1 1 1 0. Okay, it
Okay.
will make the next bit active. So this keep on, if it is, but keep on like doing that. Similarly, do like this at the bottom. Okay, so yeah. So next question we'll see. See, next question. Just read the next question. This is basically 2 kilo ohms. So it is showing. It is saying deflection. Determine the deflection of the ammeter. This is an ammeter. Okay, with a full scale deflection, it is showing that full scale deflection of 1 milliampere. So when the switch, now when the switch is at 2 kilo ohm, the deflection of the ammeter. So they are asking, when the switch is at 2 kilo ohm, what will be the deflection of the ammeter, and the full scale deflection of the ammeter they have given it as 1 milliampere. So now they are saying consider resistance of the offset voltage compensating network to be 10 ohms. Uh, okay, I will tell you what is that. But yeah. So first of all, by the way, any idea how to solve this? Okay, I will tell you. See what is happening. So first of all, we will make use of this information, that is full scale deflection of 1 milliampere is given. So what, and when we'll get the full scale deflection? Only when the current is maximum. Okay. So when will be the current will be maximum? Then when the resistor is minimum. One thing. So we are getting I equals to 1 milliampere. That is the full scale deflection. So this I can, when it can be 1 milliampere, when the switch would have been at the lowest resistance value, that is at 1 kilo ohm. So we would have one V input, any whatever the input voltage here would have been V. Let's say it is V in, because we don't know where this resistor is, like where the potentiometer, this wiper is at. So we don't know where it is. So that's why let's say it was V input, the input voltage here it was V in. Okay, so now for the full scale value, full scale deflection, I equals to 1 milliampere. And what is I? I is V in divided by 1 kilo ohm. This is same I which is going here. So it is 1 milliampere. So V in is what? 1 volt. So we got first of all we got the input voltage, that is 1 volt. Now they are saying what will be this deflection of the ammeter when it is 2 kilo ohm resistor, when the switch is moved to 2 kilo ohm. Here it is. Now it has been removed from here. Now they have given it to 2 kilo ohms. So now we know the value of V in. Now the question is very easy. V in by 2k equals to what? 1 by 2k. So it will be 0.5 milliampere. So it is basically half scale deflection, because we were getting full scale as 1 milli. So this is 0.5 milliampere, that is half scale deflection. Similarly, you can comment also, like for 10k it will be what? zero point 0.1 milliampere, that will be like yeah, tenth of the deflection, something like that. But the answer is B. Okay, half scale deflection in the ammeter.
Sir, it depends on the connection I made, sir. If it is
Switch.
connected to the 2 kilo ohm, it is off. If it is connected to the 1 kilo ohm,
No, nothing is off on here. It's just like see, we are giving some supply, okay, and here it is like when we are connecting this to this. So basically, we are getting the maximum value for this ammeter. So ammeter is having some limitations. It cannot go beyond that. So accordingly, we have arranged these things. Okay. So we cannot
yes,
go. Huh.
eh, eh, uh, because current is 1 milliampere is fixed, no, sir.
It is full scale. If we go for less, let's say 500 ohms, then it will damage this ammeter. That's all. or not damage.
Sir,
It
according to the connection, that full scale off scale is not will not decide, sir.
we see
Here
that's what like you would have to think on like based on the logic that okay, full scale can only happen when the current here it is maximum. Okay, and that can happen when the switch is connected to 1 kilo ohm. So that's why, because it cannot connect to 10, 13. We have only three, four options now. So
uh,
based on that, like we measured the
if
V.
it is four, then it quarter scale is also possible, sir. Like
Ah,
4 kilo ohm resistors.
quarter also.
It depends on the connection where we connecting the resistance, right?
Yes, yes, yes.
Yeah.
Okay.
Thank you, sir.
Yeah. So this thing, the initial part we did because why we did because we don't know what will be the input value. Otherwise, if we know that okay, let this is 50%, so then we can calculate okay, what is the voltage here, drop voltage at this potential divider. Then we can calculate here, like the voltage here. Then we can easily solve. But since we don't know that value, that's why we took help of this thing, full scale deflection. Okay. Yeah. Yeah. Any doubts?
Sir, 1 volt is the maximum voltage, no, sir, that we can apply in the input
Hmm.
to get a full scale deflection.
Wait. Yeah. No,
But they
but
didn't
no, no,
mention.
no. Yeah, based on this configuration, it is maximum.
But they didn't mention that we should take a maximum voltage.
Yeah, they like see. This is we are getting because we are assuming a condition, not assuming, we are using a condition that is 1 milliampere full scale deflection. Since they didn't mention V in, that's why we went for okay, what will be the V in voltage? V in
Okay.
is now V in is now then constant. Since once we calculated V in, then we can go for either of the switches.
Okay.
Okay. Hmm. Any other doubts? Okay. If no, then we'll go to next question. Yeah. Calculate the change in. Okay, read the question. Calculate the change in the output voltage if the photocell is exposed to light of. So they have given okay what will, so photocell is basically if the intensity is high then the resistance will be high, if the intensity is less then it will be less. Okay. So for 0.61 like lux, that is the unit of intensity, then the resistance is 1.5 kilo ohms. And for a dark like there is no intensity. Okay, I said I think yeah, for dark conditions like minimum dark resistance that is 100 kilo ohm. Okay, I think I said wrongly. If the intensity is increasing, then the resistance is decreasing. It is like that in this photo cell. So yeah, so they are saying specification they have mentioned. Calculate the change in the output voltage if the photocell is exposed to light of 0.61 lux from a dark condition. Okay, so now it is very easy. See, don't if you are seeing any capacitor in the circuit, first of all, when you if you experience any question like this, then just see what is the input supply. If it is DC, then don't fear, like don't bother about capacitor, because DC this will not do anything then. Okay, so first of all, that you should make things clear in the question. So here, since it is DC, so this capacitor will have infinite reactance, so it will not come into play. So then we have a very simple network. First of all, one condition is what? When we have 1.5 kilo ohm resistance of uh, this photodiode, and we have a 3.2 volt of what this supply. So what will be the current? So we are calculating the output voltage. So then output, this is then what, inverting amplification, yeah, inverting amplification. Then it is minus RF 5.5k by 1.5k into 3.2. Okay, this is like this. So solve one condition will be this, Another condition will be what? When it is connected to 100 kilo ohms, 3.2 volts. Okay. So in this case, it will be what? Minus of this 100k. So this will be the minimum voltage we are getting in the dark conditions, and the maximum voltage will be getting at the when it is illuminated with 0.61 intensity of light. So minus point this way 5.5k to 3.2. So we'll get two values, and based on that we can say what is the answer for this. Okay, this was easy. Will If any doubts, then you can ask. If no, we can go to another next question. Okay. So
Comfort,
with
sir. Next question.
yeah, tell me.
Yes, sir. Comfortable, sir.
Ah,
Next
okay,
question.
okay, okay. So yeah, next question. Which among the following circuit has the highest input resistance? I think you can answer this. You can answer this question. Just simply write in the chat box, or you can.
Inverting amplifier, sir.
Why?
Voltage follower will means differential amplifier. No possibility is not there, sir.
Why it is not
Voltage
there?
follow.
Okay, yeah. Why voltage follower?
Um,
There won't be input resistance.
There won't be input resistance, or uh,
Directly will connect it to positive.
yeah, it is voltage follower. Okay,
Okay.
it is like this. Okay, this
Yeah.
is this is voltage follower. Inverting amplifier is this. This is this. This is supply. This inverting. Differential amplifier is this. Some supply here. This is ground. This is differential. Okay. So now tell me.
I mean,
This is differential. This is voltage follower, and this is inverting.
inverting.
You are saying inverting. Okay. Now I need the reason also. See, if
Sir, based
yeah,
on gain, I can say, sir, I can comment answer based on gain.
yeah, tell me.
Here it would be gain, right? It should be zero, right? Mine it should be V naught by V, and it should be minus RF by R1, right?
Yes. Okay. Then
Here, here,
Then voltage follower will directly connect it to the gate of MOSFET. So it is input infinite impedance.
yeah. Basically, the answer is voltage follower. The thing is, see, this each and every op amp which is being used in this configuration, the inputs of this op amp, see here, this every op amp is having infinite impedance. Not infinite. If we say practical, then it is very high input impedance. But in this case, if we have, let's say, if we have some like device here which we are connecting and we are giving to this inverting amplifier, then the current is flowing here. Okay, although current will not flow here, but current is flowing here. So it is not like that we supplied we connected any device, and then we, in order to measure the voltage of that device, this current will load this current will load this voltage, because we wanted to measure, let's say, V. But since a current flow through this device, so some drop will be here and some drop will be here also. So we will get an output which is equals to V, what we wanted to measure, but minus the drop at this R1 resistance and RF resistance. R1 minus IRF. So this is what loading is all about. This is loading. This loading is happening here. If we talk about differential also, let's say this was what we needed V here. But if we say, so this will be loaded with this thing. Okay. But if we talk about this voltage follower, if we connect a device which we want to measure a voltage, so see, no current can, almost zero current will flow through this. Nothing will flow this through this. So whatever the voltage we are getting here, we will get it here, and the same voltage will get it there at the output. That's why it is having highest input resistance. So this is so high so that it will not allow any current from whatever the device it is being connected to. So that's why it will avoid any loading. That's why this is having highest input resistance. Okay. Any doubt in this? If no, then I
Yes, sir.
will.
Next question.
Huh? Yeah. Okay. Next question I will then go. Yeah. This also you can answer easily. Just tell me the answer.
Sir, one is two, sir.
One is for two. Okay. Wait. One according input is one positive. Input two is positive. Okay. One is two. Second.
Sir, sir three is three, sir.
Three is three. Okay. You are saying input is either positive. Huh. Okay. So yeah, you are correct. So the option will be one is two, three is three. So I think A will be the answer. Yeah.
Yes, am I correct, sir?
Yeah,
My
yeah,
question.
correct, correct. So one quadrant can only see only positive supplies. Two quadrant can see positive, and one of that can see both. That is two quadrant. Four quadrant can see all the things. Okay. So this is easy. Fact-based question. Yeah. Now this question. Read the question. It is analog multiplier. We have given one input, and then we are saying uh, what is the output. This is also, I think, easy. Just tell me the output equation. V naught equals to what?
Yes, sir. V naught would be that output voltage divided by. Sorry. Okay. The current divided by current into the 10 kilo ohm resistance, sir.
No, that is fine. In terms of, see, this is an analog multiplier. So in terms of input, it will be what? Vx into Vy by some scaling factor. And scaling factor is what? V reference. Okay. This is the analog multiplier output. And since here it is, the both the inputs are same, so it is Vx of square divided by V reference. Hmm.
Yes, sir.
Now it is very easy. Just 5 sine omega t.
Yes, 5 square sine omega sine omega t would be written
Yeah.
as 1 plus cos 2 omega tt.
Yeah, you just use that identity of that trigonometric
Hmm.
identities and you will solve this question. Okay, this is easy. I think answer is C.
Sir, it should be plus, no, sir?
Plus what?
1.25 plus
No, since it
1.
is sine square omega t, so it will be something 1 minus cos 2 omega t by 2.
Yeah, yeah, sure, sir.
Okay, so this is fine. I think this is easy. No issues in there. Now next question. Determine the lower limit of integration, frequency limit of the integration for the circuit given below. So basically they are asking like the frequency. So let's say if uh, what we'll do here.
Sir, F2 would be R2 into, sir, it should be uh, it should be 10 kilo ohms into 33 nanofarad by 2 pi, sir.
Uh, no, no. It will be, wait. It will be this one. Uh, no, no. It will be like, see, the frequency limit of the integration. If we let's say if we just solve the what is that? The transfer function of this integrator. Let's see what will happen. So this is V input. Okay.
Yes, sir.
So we have V input. Let's see. This is R1. This is R2. This is C1. This is 0. So V1 by R1. V input by R1. And we have here it is like 1 by this is R2. 1 plus SC1 R2 equals to V naught. No, not sorry. This is the parallel combination of this 1 by SC1. Okay. So this is there. Now we have what? This is equals to V naught divided by R2 1 plus SC1 R2. So this will what V naught by Vi will be uh, R2 by R1 1 plus SC1 R2. So this will decide its cutoff, this integrator. That is, so the frequency will be what? 1 by 2 pi R2 C1. So just in for my case, I have mentioned here this is a R2. Okay, so this is frequency, cutoff frequency, which is 1 by 2 pi into 1k into 33 nano. So it will be what? Just calculate. It will be 1 divided by 33 divided by 2. So it will be 4 something. Wait. And kilo. No, 10 to the 6. Okay. 3. 4.82 kilohertz. 4.82 kilohertz. It will be the answer. Okay. Just solve for the transfer function and you will get this will because see if you will solve if you plot up Bode plot or the frequency plot of this, then it will be something like this. And so this will be the cutoff frequency for this integrator. Fine. Easy. This is also easy. Now the next question. What will be the output voltage waveform for the circuit when R1 CEF equals to 1 second and input is a step voltage? Assume that the op amp is initially nulled. This you can answer, I think. Just chat box or you can mic, you know, switch on your mic also. So we are giving a unit like a constant voltage that is this 12 volts. You don't have to tell anything about voltage or something. Just tell which what it will be the output of this op amp.
The unit step function.
The output, yeah. Oh, you are saying unit step function. Okay. One answer is this. Okay. Next, any
No,
other
sir.
answer?
RAM, sir.
Okay. One answer is RAM. Any other answers?
My logic is it is integrated, no, sir.
Yeah, yeah, yeah. So yeah,
If
I was.
you are giving step as input, integration of a step, it is RAM, sir.
Yeah, yes, yes. So see, we just have to see what this function, what this thing do. So if this is V input, let's say, so what will be the current here? I. So current will be V in by R1. That is I. We know what is the equation for this. What capacitor do? It normally what is the out voltage for this capacitor? It is what Q equals to CV. We know this. Then I is what C dV by dt. So it is so what is the voltage drop across capacitor? It is dV integrated over the over the dV equals to the IDT by C. So now this I is being entered here. So V voltage a drop across the voltage that is basically V naught minus of V naught. So it will be what 1 by C. I is what V in by R1 dt. Okay, this is 1 by r1c integration v input dt. Now this, what is v input? V input is our step, this a constant value, that is, let's say it is a, or let's say it is 12 only. So integration of a constant term is what? Ramp. So answer will be ramp. Okay, so it is integrated, it has integrated this. So this is also yeah, just read the next question and answer. But yeah, one more thing, wait, if this would have been like this, then answer what then what would have been the answer then? Tell me, if the input was like this. It is
It
easy.
is triangular wave, sir.
Yeah, yeah, then it will be triangular. It will be like this. Okay. Yeah.
Yeah.
Okay. Correct. Next question. Why a resistor is shunted across the feedback capacitor in the practical integrator? I think this you won't be able to answer because this is not told in the class maybe. So they are saying a resistor is in parallel. So whatever the input is, but there is a parallel capacitor feedback to this feedback resistor. This is RF. So this, there is, we use one capacitor also. So this is done basically to like to reduce the error voltage. So this is done. Okay, there is a theory behind that. Uh, Leave it. This question. Next question. Yeah, this you can tell. Wait, is here it is like 10k. These are 10k. One correction. Sorry. It is the other. Wait, I will have to check. But you can read the next question. Oh, sorry. These are all 12k. Wait, this is 12k. 12k. Don't solve this. Just tell me the state of these diodes D1 and D3. If you know that, then you can answer this. Then it will become a basic KCL KVL equation circuit. What will be the state of D1 and D3? This is D3. I don't know where D2 is, but yeah, states.
Sir, what's the answer for previous question, sir?
Previous.
Theory question.
To reduce the error voltage. But you don't if you go little, if you want to dig deeper into this concept, then it is fine, but not related to this this course. Okay, leave it. This next question, this one, just tell me the states of the diode.
During positive cycle, D1 will be in conduction mode, sir. And
Okay, you are saying, anyway, okay, it is only positive here because it is only one peak it is given, it is not sinusoidal. Okay, you are saying, let's say positive cycle. Okay, what will be D1 will be
will be in conduction mode, sir.
on. Okay, and D3?
D3 I'm thinking, sir.
Yeah, others can also tell.
D3, sir, my logic is correct or not? I know, sir. But output voltage is connected to that. Output voltage is connected to the P is connected to one side, and one more side is connected to the resistor. If it is negative at this V2 terminal, then D3 will be in a conduction mode, sir.
If it
And
is
we will
negative
not
at
be
yeah, that
at
is the basic concept. But then, yeah, if the diode's cathode is at negative, this is positive anode, then it is on.
hmm.
Then
But
after this, what will be the anode and cathode voltages, so that we can comment on their states. So how you will tell? Others can also answer. Any guesses? Any random guesses?
If it is,
Max,
we can take two conditions, sir. It is on and off condition. During off
Yeah.
condition, we can we'll discard
We-
it. It is open circuit, no, sir. If it is open circuit, we'll calculate that voltage, and if it is on, while taking a D3 as a conduction state, we'll take two, and we can compare like that. Is that
Okay,
way, sir?
Prashanti has written both will be forward bias, non-inverting amplifier. Yeah, it is correct. Both will be forward bias. Can I get the logic? Both will be on. That is correct. One thing you have been cleared, but now can somebody explain by how?
so maximum voltage of V1 is from 0 to 6 volt.
V1. Okay,
Then,
0 to 6 volts. Okay, it is divided 0 to 6 volt.
then V2 is also from 0 to 6 volt.
Okay, but then you
Then
can do this thing only
current will
when,
be the
whe-
opposite direction,
but then you can do this thing only when you know that there is a feedback,
negative bias. Yeah.
activated feedback. That we can only tell when we know that what state this diode
Diode
is
is
in.
on.
So we cannot comment, okay, this is zero. So simple way, if you what I do normally, it is very simple. Like whenever you get diodes in an op amp circuit, what you do, just consider that op amp to be an comparator, to be a comparator. So we will assume that this op amp is a comparator. Okay, first thing. Now we'll first comment on D1. So D1, it is very easy to say when D1, this is, we are giving positive and this is zero. Okay. So even if, like, anyway, this anode side is positive, so D1 will be on. I think that is the very easy thing to say. But then how to comment on D3? So just think, we don't have any negative feedback. We don't have any feedback network. So then what will be the state of this output of this op amp? Initially, momentarily, it is acting as a comparator. Then this is what? This will be some positive voltage because we have given some supply here. Okay. And this is what? Zero, connected to the ground. This is zero, this is positive. So what will be the output of this op amp? That is plus V set. Okay. So plus V set will be seen by the anode side of this diode. And here it was zero. So this is positive, this is zero. So that means it will be also on. So just consider op amp to be in on state, and then, oh sorry, op amp to be like in open loop configuration, like a comparator. So I will just write down op amp comparator. Momentarily remove the feedbacks, remove everything, then just comment. Then you can decide, okay, what is the state of the op amp. If this logic is clear, then we can proceed. This will make things easy for you. Okay. So I think this is okay, straightforward. Then it is very simple. Then you don't have to do anything, and you will get the answer. Okay, then simple open circuit. Fine. I can move forward, I think. Okay. Yeah. So now next question. Yeah. How to detect the negative peaks? So these questions, yeah, some mixed questions. So this is a peak, like peak detector something. So they are asking how to detect the negative peak of the input signal. So answer me. Just think and read and think. First of all, just tell me right now what it is doing. Then answer like how you will do that. If you know that what right now it is doing, then you can answer like easily what how you will do that, how you will do things in negative peak. Let's say you gave a positive peak. So now what it is doing?
Non-inverting amplifier.
Hmm. See, uh, if you are saying non-inverting amplifier, I think that is not completely correct because here in this path there will be no current. But in yeah, but in non-inverting amplifier, the configuration is like this. Here is a voltage supply. So some current flows from the feedback. So here it is kind of a voltage follower. This resistance is simply given like that. it is having its own importance, but let's remove like neglect like. So I'm asking, let's say if I gave a positive peak, then will it detect its peak or not? First of all, yes or no. If I give positive peak input, forget about the question. Just if I give a positive peak input, forget about the negative peak, only positive, then will it detect peak? Will it detect peak at the output? Yes or no? Yes or
Yes.
yes, okay. How?
So if we give the positive voltage, then capacitor gets charged.
Yes, yes.
Then we'll get a peak voltage over there
Yeah, yeah,
at the
you are
output.
correct. So, but can you comment on the diode conditions?
D1 will be on and D2 will be off.
Correct, correct, correct. So this also again we can go with that comparator logic. See, let's say we gave positive, so this is positive and this is ground. Okay, this is ground. This is acting as a comparator. So this here will get P plus V set. So this plus V set will make this diode off, will make this diode on. So once it make this diode on, then this feedback will come into picture. Okay, and we gave a positive, so here plus minus it will, the capacitor will get charged as plus minus. And once, so see what will happen. So once it is charging, capacitor charging, once it gets at the peak value, the input will start discharging, but the capacitor will keep on there, because we are assuming that the time constant is very high, so it will remain like this. Now answer the question. So now you, one part is clear what now, right now circuit is doing. Now you answer the question. So now you have to detect the peaks. Now you have to detect the negative peak. So what you will do based on the options? Now you can easily answer.
Reversing both D1 and D2.
Correct. Correct. D1 and D2. So what will happen if we reverse this? Simple. So if a negative peak is there, then this is what? This is what? Negative. So this will be negative. Then here it will be minus V set. So if we have reversed this diode, then this will be what? Off again, and this will be on again. So we will get a negative peak and this will be charged to plus minus plus. Fine. So both the conditions, the diode should remain on. The D1 should remain on and the D2 should remain off. Okay, if you have doubts, then I can explain this question again.
So like what is the use of D2 diver?
D2C. So when uh, I will tell you the positive supply. So when you give the positive supply, let's say positive peak, so here is plus V set. But in this case, if you gave a negative peak, so here it will be minus V set. So it will make this zero. So there will be no output. So this is only a peak detector for positive or negative peak, but not both at the same time. It can do only one operation at the same time. So if the diodes are like this, mention the like this, so then it can only detect positive peaks. If a negative peak is given, then it will give that as zero voltage. So that is the importance of D2. It will make that ground for a negative peak. Got it?
Yes.
Okay. Others having doubt in this? No. If no, then we can next go to next question. Yeah, compute the passband gain high cutoff frequency for the first order high pass filter. Yeah. So this like if you have any questions related to like frequency response or like pass band gain, something like that. If you know the direct formulas, then it is fine, but not every time this direct formulas works. Like if you are good in that, then you can remember that. Otherwise, you can go with simple transfer function. So let's say this is v1, that this is v2, and transfer function is basically v naught by v in. So if you are stuck with any question which is involving frequency response, questions related to bands of frequency response, and you don't have any idea, just solve this thing v naught by vi somehow using kcl kvls whatever you have. Then you can answer at least some you will be able to get to some part of that question. Okay, that is when you don't have no idea about this, what is going on in that circuit. So best thing is to do calculate for the transfer function. So transfer function for this will be what? We will calculate that first. Then we'll see what we can, how we can answer this. So what? So V2 is here, V1 is there. V2 equals to V1. One thing virtual short is happening here. So V naught will be what? Since these are 10k 10k, so this will be V naught by 2. Okay. So this will be V naught by 2. Then yeah. So V2 equals to V naught by 2. What will be the V1? V1 will be, let's say this is V input. So V input 1 by SC1. Let's say this is C1, this is R1. 1 R1 1 by SC1. So it will be VI SC1 R1 plus 1. Okay. So V1 we can equate with V2. So V naught by 2 equals to VI 1 plus SC1 R1. That implies V naught by VI is what? 2 times 1 plus SC1 R1. So now they were asking for compute the pass band gain. So the gain is what? From transfer function we can say 2, it is the gain, and high cutoff frequency is what? 1 by R1C1, 2 by. Okay, so this is what? This is a low pass filter. Low pass filter. So if you have to comment from this also, you can say when you make this S0, that is frequency 0, then it will give a definite gain. But when you make this S infinite, that is frequency is infinite, then this will become 0. This thing will become 0. Or if S equals to infinite. S is basically frequency. Okay, so you can then answer. I think this will be the answer. Any doubt in this? If no, then we can go to the next question. See, they have just compute the voltage gain for the following circuit with input frequency 1.5 kilohertz. So they have just changed the location of this capacitor. So in this case, again, go with the this one transfer function. What it will be. So since they have changed the location of the capacitor, so then we'll solve this. Then what will be the, so this is again V1 V2. So then V naught will be what? V naught will be V V2 will be V naught by 4. That is simple, like you can, here it will be V naught by 4. V2, this is V1. Okay, so this will be simple voltage divider. Then V1 is what? Uh, yeah, so it will be, so V input into, let's say this is R2 C1, sorry R1. So V input into R1 1 R1 plus 1 by SC1 equals to V1. This is V naught by 4. Okay, because this is equals to V2 virtual short. Okay, here it is happening. Then V naught by Vi will be what? If you can equate this, it will be R1 4R1 R1 plus 1 by SC1. So this will be 4R1 SC1 R1 SC1 plus 1. So what is this? Which type of filter is this? Can somebody tell me? Somebody.
I
High pass.
High pass.
Oh, okay, why?
because
Your voice is yeah.
So one pole and one zero.
One pole, one zero. Yeah, that is also one way to easy way to tell this, that when s equals to zero, that is frequency zero, frequency equals to zero, then this will become zero because it is having one zero. If s equals to infinite, that is f equals to infinite. Okay, then what will happen? It will be some limited value, some a constant value, because if we remove s from here and make it a denominator, then it will be like this: for r1c1, r1c1, 1 by s. So this is infinite for finite, for infinite frequency, then this will be only 0, but we will get some constant value. So from this also you can tell that this is what high pass filter. Here similarly this was low pass filter, this was high pass filter. Okay, so based on that they need this gain, so v naught, so gain is what, basically modulus of v naught by vi. So whatever you will substituting the values, so you will get 4 r1 c1 omega 1 plus omega r1 c1 square under root, by using this thing. Okay, this thing is I think clear, simple, taking the modulus of that. And for dB you will use 20 log of v naught by ve modulus. That you can answer then this question. Okay. uh, I think if any, just see that if you have any doubts, just then ask me, then we, otherwise we'll go to the next question. We have I think two questions more left only. If no, then we will go to the next question. See, determine the angle for the given circuit diagram if the frequency of the input signal is 1 kilohertz. Okay, so first of all, I will derive the transfer function for you in this question. Then I will ask you one question. First of all, let me derive the transfer function. So let's say this is V input. Hmm. This is V1. This is V2. I think the transfer function I was having somewhere. See. Also, it's simple. V1 is equals to what? V1 will be V input into 1 by SC1. This is, let's say, C1, R1. Okay, everything is R. So this is R. This is also R. 1, this one is R plus 1 by SC. So this will be Vi SCR plus 1 V1. Now what will be V2? V2, this one, V2 will be what? V2 minus, I'm just simply using KVL here at this node. Okay, so V2 minus Vi divided by R plus V2 minus V0 divided by R. So V2 will be what? V2 will be Vi plus V0 by 2. Okay, simple. Now we'll equate this with V1 because V1 equals to V2 virtual short. So we will get Vi SCR plus 1 equals to Vi plus V0 by 2. So if we solve this, we will get finally V0 by Vi as equals to 1 minus SCR1 or R, simple, 1 plus SCR. Okay. Now, now comment on what type of filter is this. Hallo Herr Silber, ich wollte nur noch mal dran erinnern, bitte heute alles ganz, ganz gut abschließen. So V naught by Vi is 1 minus SCR1, SCR divided by 1 plus SCR. So I want like which type of filter is this? Die abschließbare Eingangstür ist jetzt erstmal bis morgen oder übermorgen nicht da, die muss weitergeleitet werden. Dann wäre es nicht schlecht, wenn wir hier alles abschließen. Was? Aber das nicht so an der physischen Welt.
So band stop.
Which one?
Band stop.
Band stop. Okay. Band stop, you are saying. Why?
So because when S is 0, we get 1 by 1.
Huh?
Means at lower frequency, we get gain 1.
Huh?
And
Huh?
when S is infinite, also we get 1 by 1. So again,
We
high
get some.
frequency
Huh?
getting 1 by 1.
Yeah, yeah. So I think
So
that is
maybe in the
band
middle,
pass filter. Huh? Band stop is I think this na. It band pass is this.
yes, so it's bands. I think it's band stops.
Uh, so we are getting sorry, okay, okay. Oh sorry. So then you are saying wait. Yeah. So band stop, yeah. So you are saying there can be some value where it can be zero also. So can we solve that? Okay. So that means like V naught by Vi will be zero. So 1 minus SCR1 plus SCR1 equals to 0. 1 by SCR 1 by RC equals to S. That is like omega will be with this value. Yeah, kind of band stop. Huh. It will be kind of band stop. Hmm. Yes. But yeah. Hmm. Okay. Yeah. So it is kind of band stop, but normally this is an all pass filter also. So that's why I was thinking if this gain is becoming zero, then it will be, if it is becoming zero, then is the gain is dropping that much or not to make it band stop. Okay, but yeah, okay. Now, if this is this one, then so then you have to comment on the angle. Then you can simply solve this. So the angle for this will be what? Tan inverse uh, omega c r1 minus, because this we have minus sign, minus because this at the bottom, then it is tan inverse omega c r1, so it will be minus 2 tan inverse omega c r1. Okay, so using the values of omega c and r, we can solve the theta. So they are asking for the angle, you can solve this. Okay, any doubts in this? If no, then we can go for the last question. Yeah, here this is not given, forget about this. Now solve this. This is easy, I think. You can answer this. Oh, oh, IL is this basically. They haven't mentioned IL. So I think this is easy. Find the current IL flowing the circuit given below. Okay. Oh. So see, I think they haven't. They should have mentioned the reference voltage also, because see, simple. This V naught is what? Vx into Vy by V reference, but they haven't mentioned anything about V reference. Okay, no issues. 13 square divided by V reference, because this is the input, 13 square. Then what will be the IL? IL, then it is easy. V naught 1, let's say this is V naught 1. IL is V naught 1 by 12k. Okay, so 13 square V ref 12k. I think yeah, there should be V reference also, but it is not given. So okay, but yeah, the approach is like this. Okay, so yeah, yeah. So any doubts in anything, or otherwise we'll end this session here. Yeah. If you have any doubts, then yeah, just ask me.
Sir, could you please share that PDF, sir, in discussion forum? Don't forget, sir.
Yeah,
It would be very useful.
yeah, PDF, yeah, PDF I will share, and this I will upload that. You have YouTube link also, na? Wait, I will again
Ah,
give
yes.
that in the chat, this chat. Wait. So this is the recorded thing, and I will just share you the link to that my YouTube channel. Wait. Yeah. Just once check if it is working or not.
Yes, sir. Working, sir.
Okay. So then yeah, I will
Sir,
upload this video. Huh?
previously you said no, sir, that PDFs and all from week one to just for a
The assignment question PDF, yeah, that like what I like solve like this, na, this one, like this I solve. So this I will share you.
uh,
This I will share you on the discussion forum so that everyone can see. And but
hmm.
I cannot guarantee that it is from the week one, because from the starting of the weeks I was solving that separately, so that you can find in the YouTube videos, in the last part of the YouTube videos, last duration. But otherwise I will send the PDF from where which I started doing like this. Okay, I think it is from week 7 or something. I'll share from that.
Oh, okay, sir. Sir,
uh,
don't forget, sir. It would be very useful
no,
for
no,
me.
I will share after this. I'll share.
Yes. Thank you, sir.
Yeah, welcome, welcome. All the best for your exams, and I hope you score good in that. And don't worry about the like the questions or whatever, like it's just an exam. Okay.
How many questions will be there?
I don't have any idea about the
50
format or.
questions.
Oh, yeah, I think they might have shared with you. So maybe, yeah, yeah, welcome,
Can we get
welcome.
previous year questions? Previous year
Previous year,
question
I
paper.
think this is the second time this course is running, so even we don't, and I think professor will not share the questions from the main question, main paper, question paper, and this second time running, so I'm not sure whether any on net also you can find the previous year. So
Okay.
yeah,
Sir,
but
in the
just go through the country. Yes, yes, yes.
reference, there's one book, no, sir, like in the links.
Ha ha.
It's mixed, no, sir.
That book is uh, yeah, yeah.
Only the PPTs, only the PPTs used for the
Your
teaching.
voice is what you're saying.
Like in the book, sir, even the only the slides are included, no, sir,
Ha, yeah.
along with
Like
the
whatever the
transcript,
slide content, it is there. Only that is
along with
there
the
in that.
transcript. Like, can we
Ha.
get only the PDF separately of the presentation?
This presentation, I don't know why it is not being shared. But see, if you will see the presentation separately, then you will not get anything because I write very badly. Uh, because you will not able to get what I wrote there in that. See, if for the example, see week 11 content. See this things like this I have written. So this you can only get once you are 10. Like if you will see the YouTube videos, just run that at 2 times speed. So PDF, this PDF itself, like it is there in that video, and whatever I'm saying now, so you will get through that. So that is better way just to in respect to just going through these this content, because I'm
So like
very
not these like professor used for teaching slides, no, sir,
teaching slides.
in the videos teaching slides.
That is I think in there in that book.
It's along with the transcript, sir. It's not separate. It's mixed.
Okay. I afraid I think there is no separate file for that. Yeah, yeah. I think whatever links you are access to now,
Yes.
that same link I have access to.
Oh,
So yeah, yeah, yeah. But I think book will be fine. Just to go through that whole of the lectures, book will be fine.
okay, sir.
Yeah, yeah.
So can you send some more questions?
Okay, I will try. Yeah. Otherwise, yeah, I think this much is sufficient. Whatever content you have been went through that do that, na, that will be fine. So yeah, that will be like I have solved extra questions in the previous video also, which have been uploaded, so you can check that also. There are ADC and DAC questions of gate, so you can see that YouTube lecture week 11, and before that also I have like solved extra questions in some weeks, so you can check that.
Okay.
I think this much will be sufficient. I hope so. Okay.
Okay.
Yeah. Okay. Thank you for your patience and all. So I hope you do well in the exams. Okay. Yeah. Okay. So I will end this call. All the best.
Thank you, sir.
Yeah. Welcome.